Hi all, welcome to our YouTube channel Math Universe with Dr. Naseer Ahmed. Today we're in the last chapter, chapter probability for annual board examination. The chapter probability will be the last chapter for the crash course of second PUC which I promised. Okay, so let's move on to the last chapter. Chapter probability, and we are in PUC and we can expect 7 plus marks. See, as you're aware, probability is also there in first PUC. So I would like to recall some of the first PUC concepts so that things will be very clear. Okay, for a while. Yeah, fine. I just made sure whether the sound is full or not. Mic. Okay. Now let us try to recall some of the things which are very basic. In no time we can cover that, and then we start with the second PUC concept and then the problems from the model question papers. Now coming to first year probability, the basic which I'm going to recall the basics. First, let us understand what do you mean by sample space. Sample space is defined as all the possible outcome, all the possible outcomes of a random experiment, and it is denoted by capital letter S. The best way to learn this chapter is we can compare this chapter to chapter sets. There we had universal set where it contains all the subset. So in place of universal set we have got sample space denoted by S. There it was capital U in chapter 6 for universal set. So it's all the possible outcomes of a given random experiment. Now the question is, what is this random experiment? Random experiment. What is this random experiment? Listen carefully. Any experiment satisfying two conditions. How many conditions? Two conditions. Condition number one, there should be more than one outcome. There should be more than one outcomes. Condition number two, in advance one should not predict the outcomes. See, let us try to understand with an example. The best, easiest example, tossing of a coin. When you go for tossing of a coin, okay, example, tossing of a coin, what will be the sample space? When I say tossing of a coin, I am tossing only one coin. And when I toss a coin, we are going to get two outputs, either head or tail. H stands for head and T stands for tail. And we enclose all the possible outcomes with a floor bracket, same like chapter 6, separated by comma. Each of these are what? Outcomes, and it is, since all the possible outcome, it is nothing but sample space, capital S. Now, see, when I'm going to toss a coin, surely we have more than one outcome, head or tail. So the first condition, there should be more than one outcomes. It is satisfied. Second condition, we are not able to predict the outcome. For example, in cricket, when the play started, I mean to say in the cricket, when they go for tossing of a coin, both the captains, among the two, one captain is going to guess the outcome and other is going to toss. So they are guessing it. So the guess can be sometimes correct and sometimes wrong. Depending on that, sometimes the captains win the toss, sometimes they lose the toss. That's what, no, in advance we can't predict the outcomes. That's what the random experiment is. Now here, these elements which are present in sample space, these elements are called sample points. So what are sample points? Sample points are these, it is elements of a sample space. Okay, So this is a very basic primary thing about sample space is by capital S, and it is all the possible outcomes of a given random experiment, and random experiment we have defined, and one example we have taken. Now let us move on to events. First, make a note of this. Okay. Now let us understand what do you mean by events. See, as I said, the best way to learn this chapter is to compare with chapter sets. There we had subset. A set A is said to be subset of B if all the element of A is contained in B. Similarly, what is event? It is any subset of sample space, and we denote subset by capital letter A to Z except S. S is for your sample space. So any event, what is event? Any subset of sample space. What is event? Any event, right here. Event is a subset of sample space. Now, let us take one example. Again, if I go for tossing of a coin, now in that, if I say in tossing of a coin, example, tossing of a coin, and then I'll define one event A, getting what? Head. So now, coming to the solution, sample space, tossing of a coin will be either head or tail. And my event A is what? Getting head. Do we have head here? Yes. So, H, and this is subset of what? Sample space. Now, let us try to understand types of events. Types of events. So, in this, the first type is impossible event. Now, what is this impossible event? An event is said to be impossible if it is equal to empty set. What's the meaning of that? That it has not occurred. Now, occurrence, when we say whatever the output we are getting, it should be in the sample space. When I say sample space, it should be an element in the what? Given experiment. That outcome should occur. Okay. So now, sir, can we give an example? Yes. Now here, if I take this example, tossing of a coin, let us suppose that for this, now whatever I'm going to talk about the examples, now I'm going to take this as the question, that tossing of a coin is the question there. Now, let us suppose that I'm going to take one event B, getting 7. But in tossing of a coin, I will not have 7, due to which B will be null set, nothing but it has not occurred. It has not occurred, nothing but impossible event. Next comes sure event. What is this sure event? An event is said to be sure event if the event A is equal to sample space itself. Nothing but all the element of sample space and the given event both are what the same. For example, I'll just try to write A, B, C, let's use all the letters. And suppose C is getting head or tail. Now, right here. So the elements of the outcomes of the C, I should get head or tail. Head do we have in the sample space? Yes. Tail do we have in the sample space? Yes. So this is what? H comma T, which is same as what? Sample space. Okay. Next comes simple events. Now, what is simple event? Or we can also say elementary event. When do we say an event is simple event? An event A is said to be simple event if number of outcomes are 1. Number of outcome of the given event is 1. For example, let us suppose I will define one event D here. That is, D is given as getting what? Tail. And do we have tail in this? Yes. So D is equal to T. So here number of outcome is how much? 1. Since number of, it's not number of element here, we should say number of outcomes. And how many outcome? Only one, that is tail. And it is 1. Therefore, it's called simple event or elementary event. Similarly, we have got one more, compound event. Let I do one thing. Let I erase this side. Compound event. What is compound events? Events having more than one outcomes. If number of element in the given outcome, I mean the number of events in the given outcome is more than one. For example, let us suppose this only. Okay, this can be an example of what? Having more than one outcome. You can see I got two outcomes. Okay, this particular example is both short event as well as what? Compound event. Okay, but need not be the always that both will happen. Okay, it can be different also. I mean to say, every short event need not be a compound event, and every compound event need not be a short event. Okay, fine. So this is that. Now comes, having understood this, now it is also tried to go for some of the operations. But I erase this. But I give a pause. Dear students, now let us move on to algebra of events. Does I write here properly? Yeah, algebra of events. See, same as school is no, as soon have learned numbers. Yeah, fine. So same thing like school days, after learning numbers, you have to learn how to add, subtract, multiply, divide, nothing but algebra of numbers. Similarly here, after knowing types of events, what are the different operations can be performed, the algebra of events. So here, the first one, complement of an event. So let's suppose that I've got an event A. So if I take the complement, say like in what's that? Chapter 6, we had A dash or A power C. It is set of all element X such that X is present in the sample space, but X should not be present in the same event A. So if I go with the Venn diagram, see carefully, this is a sample space. Hope this is recording. Yeah. A sample space. So if I say that this is the event E, it means A, then this outer region will be what? A complement. Okay. Next, union. If I've got two events A and B, union is denoted by small letter U. Say A union B is set of all element. Okay, or here outcomes. Here is outcomes dancing element such that X will be present. The outcome should be present in A, or it should be present in B. Okay, or we can say it should be there in both. Then comes intersection. Let us quickly recall all this. Coming to intersection, it is set of all events. First, A intersection B is set of all the events X such that X is present in A and X is present in B. Next is fourth one, what we usually say difference. See, A minus B, which is nothing but set of all events such that X is present in A but X is not present in B. We also write this A minus B. See, try to understand this. What's the meaning of this? Present in A but not in B. Present in A but not in B. Present in A and not in B. Similarly, if I say B minus A, it means present in B but not in A. So not in A but present in B. Okay, these are the different operations which we have got. And then next comes the axiomatic. Okay, before this, mutually exclusive events. So operations done. Now what is this mutually exclusive events? See, let us write capital E here. Two events. If I just talk with respect to two events, okay, first we discuss with respect to two events. Two events are said to be mutually exclusive if the intersection of both those events are what? Empty. If I take with the help of a Venn diagram, So event A is here, event B is this. So they should not be, both should not occur simultaneously. That's the meaning. Let us suppose that I've got 3 events. If I talk about 3 events, then pairwise they should be disjoint. When I say disjoint, don't forget disjoint means intersection will be empty, nothing but there should not be any common occurrence. So it also means that A and B should not occur simultaneously. Coming to our independent event of second PUC concept, we'll be having always some talk about this. Okay, so let's understand this one properly. So if I've got 3 events A, B, and C, we say it is mutually. I mean to say this are all called mutually exclusive events. Exclusive events. If pairwise they should be disjoint. Nothing but if I take A intersection B should be empty. Then A intersection C should also be empty. Coming to B intersection A is same as A intersection B is commutative, you know. So B intersection C should also be empty. Okay. Only then we say similarly C intersection A is already there here. A intersection C and C intersection A both are same. C intersection B same as here. So if I take a Venn diagram and understand, okay, sample space, I mean to say yes. So here this is event A, this is event B, and this is event C. Okay, kindly make a note. Now let us try to understand this mutually exclusive events in general. Let us suppose that we have got the event E1, E2, E3 up to En, and all these are what subset of sample space. Only then we say it is events. These are said to be mutually exclusive, provided if I take pairwise Ei intersection Ej, this should be empty where I is not equal to J. Surely it should not be equal. If it is same events, surely it will be non-empty only, provided the given event is non-empty. Okay, so if I just go with respect to a diagram for this, see carefully sample space. So here it can be event E1, here it can be event E2, here it is event E3, here event E4, like this. You can have so many like this moving on, and somewhere event En. So you can see pairwise they are never have anything common. Okay, now comes one more exhaustive events. So if I just talk with respect to 2 events again here, 2 events are said to be exhaustive events. A and B are said to be exhaustive events if I take union, I should get sample space. Now in Venn diagram, now see, in Venn diagram I cannot take only A and B in the form of a circle, because if I take the union I'll get only A and B, I'll not get the entire sample space. So now we have to just give something like this: A here, B here. This is event A, this is event B. Together if I take union, I'll get what? Sample space. And they may have common also. Okay, coming to 3 events, when do we say they are mutually exhaustive? So if I take union of all the 3 events, it should be what? Sample space. So I can just have one sample space here. Now again, if I take union of these 3, I'll not get what? The rectangle box. So that's what I'm saying. We should come out of usual circle notation. That's what you can see here. Okay, that we are not there with form of a circles here. So let us suppose one event A here, one more event B here, and there's one more event C here. So this entire thing is event A, this entire thing is event B, only this part is event B, and this is entire C. So there are some common between A and C. So if I take the union of all the 3, A, B, C, I get sample space. Okay, fine. So if I talk about in general, this was in general. Similarly, in general, if you speak, we are going to have union of all the events I running from 1 to n. If I talk about n events, whichever present E1 to En. So if I say I is equal to 1, it is E1. Then this symbol stands for union. I equal to 2, I'll get E2. Then union, because the symbol put I equal to 3. Like this, if you go, we get the sample space. Okay, I hope this is clear. Kindly make a note. Okay. Now, dear students, having understood some of the basic things, let us move on to next basic thing, that is axiomatic approach. Axiomatic approach to probability. Dear students, now let us move on to axiomatic approach to probability. See, this word axioms or postulates are not new for you people. In school days also, you had something like axioms and postulates in geometry. Nothing but these are those results which can be agreed without any proof. Now here, coming to probability also we have got as such. The first axiom is probability of any event EI is always non-negative. Mean to say that it can be either positive or equal to 0. Nothing but it should occur or it should not occur. It can be negative. Next, probability of any sample space is 1. Third, if A and B are two mutually exclusive events, then probability of A union B will be equal to probability of A plus probability of B, provided A and B are mutually exclusive. When do we say any event is mutually exclusive events? The intersection between them should be empty, nothing but they should not be simultaneous occurrence. Now, before we just go ahead now, let us first understand what is probability. Probability is defined as, what is probability? It is a function. See, you recall in the first PUC, even second year also, function we have got f is a function from A to B, where A is known as domain and B is known as codomain. And whatever the image we have got, f of A we call as image. So, what is a function? It's a real, what's a function? It's a special type of relation where every element have unique image. Similarly, probability is a function whose domain, now see this, probability, no, here function I taken f, for probability I take p. It is a function whose domain is power set of sample space. Power set, recall, if A is a set having the element A and B, power set means collection of all the subset of A. What are the subset of A? Empty set, then set A, small set A, the small set B, and then small set AB. Nothing but this is nothing but A itself. This we call power set and we denote as P of A, collection of all the subsets of a given set. So similarly here, probability is a function whose domain is power set of sample space. So P of S. P stands for power set of what? Sample space. Nothing but collection of all the subset of sample space whose range is closed interval 0, 1. So it is all the possible outcome of a given experiment. And here the domain will be power set of sample space and the range will be closed interval 0 to 1, and it's a real valued function. So as far as you can see, the output is always a subset of real number. Now having this, now many of the things can be understood. Let us try to understand this one with the help of one more definition, that is probability of equally likely outcome. So probability of equally likely outcomes. Let us suppose whatever the experiment we perform, and coming to PUC, I got almost every experiment to be equally likely outcome. And if I got any event A which is subset of sample space, obviously, then the probability of any event A is favorable outcome divided by total outcome. Favorable outcome of the event E, or here A of the event A, divided by total number of outcome in the sample space. Now having this information, we can understand this much better. Now come here, probability of any event EI is always positive or equal to 0. You can just see now how to get this justified. See carefully. As we know, let us just take as a note, okay. we know that A is subset or equal to sample space. Y equal, it can be sure event also. Okay. Now, if I talk about number of number of events in A, that will be either less or equal to number of events in sample space. And if I divide by number of element in sample space, and sample space being a positive quantity, inequality will not change. Don't forget, inequality will change only if you divide or multiply by a negative number, and here it is positive. So when I divide, inequality will not change. So n of A divided by n of S, n of S by n of S will get cancelled, get less or equal to 1, and number of outcome cannot be negative, so this is always greater than 0. So this is what? Probability of any outcome. So 0 is less or equal to probability of any event A is less or equal to 1. So probability is always going to vary from 0 to 1 closed interval. That's why we can see the range here. And this is also justifying this point that probability of any event is always non-negative. Yeah, it's non-negative. And how come probability of sample space is 1? Very simple. This is the first note. Coming second note, if we talk about probability of sample space, come on, put in this formula. And surely here probability of the sample space should not be equal to 0. See, mathematically, since it's n of S is there in denominator, we said should not be equal to 0. If this is 0, we'll get undefined. But the other way, this is mathematical way, that if denominator is 0, it will be undefined. But one more, if denominator n of S is 0, it means that S has not occurred. When there is no sample space, there is no event. There is no experiment at all. Okay, that's the reason n of S should not be equal to 0. So now P of S, in place of A we have S. So wherever A is I put as S. So favorable outcome in sample space divided by total number of outcome. Since both are same, both will get cancelled, get 1. Therefore probability of sample space is always equal to 1. That's what here. And this one more thing that I just comment here is third point here. In general, probability of A union B is given by probability of A plus probability of B minus probability of A intersection B. This will be one of the important formula for us. Okay. Let us suppose, sir, what about if I got 3? One more note what I want you to remember is, if you take the sum of all the probability values Pi, I running from 1 to n, nothing but element to event, nothing but when you take each sample point, and if you take the sum, it will be equal to 1. For example, in tossing of a coin, if I say the event A is getting head or tail in tossing of a coin, you see here A will be either H or T, and sample space is also what? H or T. Now probability of H is how many? Head only 1, divided by total is what? 2, because number of element in sample space is 2. And what about probability of tail? How many tail? Only 1, divided by total. Now add this. What is sum of the probability of H as well as T? I'll get half plus half, which is equal to how much? 1. And lastly, one point I will just add it here. Always remember this one more, that probability of E complement, which is same as probability of not E, is always equal to probability 1 minus probability of E. So with this, we are ready for the second PUC part. Kindly make a note of this. Dear students, having completed the basics of first PUC of probability, now time has come to start with second PUC part of probability. Now here we are going to discuss the first concept, that is conditional probability. Now what is this conditional probability? Listen carefully. See, whatever the probability we have discussed in first PUC, you have got only one particular event, okay, and you want to find the probability of that particular event, like tossing of a coin getting head to tail, or tossing of a rolling of a die getting 5, 6 like that, or getting 7. I think, but when I say probability of getting 7 when a die is rolled, it will be what? 0, because the outcome 7 is not there in the sample space. Okay, so now here in place of 1, we are going to have more than one event occurring, in which one event has already occurred and the other event is depending on the event which has already occurred. That we call conditional. A condition is given, one event has already occurred. Now just see, let us take a sample space, a diagram to understand. Here I've got sample space and I am taking two events here. This event is E and this event is F. And don't forget, this will be the common event. This entire circle represents E, this entire circle represents F, and this is the common event E intersection F. Okay, I'll do one thing, that I draw a bit more bigger. I think E intersection F is not visible. Nothing wrong with the diagram. I just want it to be still more bigger so that visibility is still more better for you all. Yeah, this is this entire circle, left one let's take as E and this as F, and this is the common event, common occurrence, that is E intersection F. Now in this, what we are saying is, among this E and F, one particular event should already occur. Let us suppose that S has event F already occurred, whereas this event E is yet to occur. Sorry. So now probability of the event E when F occurred. See carefully, the notation is very important. Whenever you see the symbol, it is what? Conditional probability. The event which is written below is already occurred, and the event which is present above, it is yet to occur. Sometimes in printing I have seen they will write like this, like numerator denominator. There is no notation, but I have seen in the typing that in question paper sometimes they write like this. Both are same, and this is probability of common occurrence divided by probability of, in place of sample space, the event which has already occurred, where probability of F should not be equal to 0. Try to understand here. Usually probability of any event A is favorable outcome divided by total outcome, that is sample space. So in place of sample space, we have got here an event F. Both E and F are the subset of sample space. So coming to conditional probability, the definition will be, let E and F be two events associated with the same sample space S, in which F has already occurred and E is yet to occur. Then probability of E when F occurred is probability of the intersection divided by probability of the event which has already occurred. And you can see, in place of sample space, we have got probability that of that event which has already occurred. So the sample space role is changed by that event which has already occurred. Okay, and if I go with this definition, so if I just simplify this, probability of whichever event is the same divided by number of element in sample space. So if I just write like that, so number of element in E intersection F divided by number of element in sample space divided by number of element in, for this one, F divided by number of element in sample space. So you can see number of element in sample space will get cancelled. So we are going to have number of element in E intersection F divided by number of element. I mean to say number of outcome. When I say element, it's number of outcome. Okay. So this will be the alternate way of writing conditional probability. And again, number of occurrence in F should not be equal to 0. If F is not occurring, so here also I would like you to point out, now I would like you to understand that mathematically, since the fraction denominator should not be equal to 0. Yeah. If not, it will be undefined. But the other reason is, the actual reason is, if this is 0, nothing but probability of F is impossible event if it is equal to 0. Impossible event means F has not occurred. When F has not occurred, there is no question of E to occur, because in this we are completely depending on that one event has already occurred and the other event is going to occur, having the same common occurrence. Simultaneously we are going to have, okay, some common things there. Okay, so having this, let us try to, and you have to remember this. See, it's not like a differentiation, integration where you have so many formulas, trigonometry. Here, very simple. For each exercise, we have only one formula. This is the formula which you have got. Now, before I go ahead with the question problem, let I go for three properties which is there in this concept. Okay, and don't neglect the property. I will be proving, but at least you remember the result. Who knows, for 1 mark they may ask which of the following is false, and that will also be helpful for CET as well. Okay, kindly make a note. Fine, dear students, now let us move on to the properties. So this is our property. These are the properties from conditional probability. Okay, now what this property says, Let E and F be events of a sample space S of an experiment. Then we have the first property says probability of sample space S when F has occurred is equal to 1, and probability of the event, the same event, okay, F and F will be 1, again what, 1. Let us try to prove this. Very easily we can prove it. See, coming to the first part, probability of sample space when F occurs. When F, I repeat, probability of sample space when F has already occurred. Recall the formula. Probability of an event E when F has already occurred is probability of E intersection F divided by probability of F, where probability of F should not be equal to 0. Now, going with this, whatever you have got in above and below, yet to occur and already occur, should be taken intersection. So here, yet to occur and already occur, if I take the intersection, I get S intersection F divided by probability of F, where probability of F is never equal to 0. Now, having understood this, recall, since S is a sample space, is it not the event F should be what? Subset of sample space. So, since F is a subset of sample space, if you take the Venn diagram, this is the sample space and this is F. F is contained in S. Since F is contained in S, the intersection between, nothing but the common between the sample space and the subset event F will be what? F itself. Because among these two, which is common? This is common. Correct? So, P of F divided by again P of F. Now, since both of them we can cancel and we are getting what? 1. So, probability of sample space S when F has already occurred is 1. So, first part done. This from here to here we have did. Now, coming to probability of sample space, probability of F when F has occurred. Okay. So, let us take that probability of F when F has occurred. Again, by using the formula, whatever we are taking, we should take intersection of both. Now, if I take the intersection of F and F divided by probability of F, again probability of F should not be equal to 0. Recall from chapter sets, what is the intersection of a set A with itself? It is A itself. So, F intersection F will be F itself. So, now both will get cancelled, and as soon as it's cancelled, I'll get what? 1. And here we have got probability of F when F has already occurred is how much? Is equal to 1. I hope this point is clear. That's all we wanted. We have got this part also. I hope this is clear. Now let us move on to the next. Okay, this is actually a generalization of what we have learned now. Probability of A unit B is equal to probability of A plus probability of B minus probability of A intersection B. Now here it is on conditional probability. The property says if A and B are two events of a sample space. See, for this to be true, no, first A and B should be a event of the same sample space. That's very important. Of it is so same sample space, and F be any event of S such that probability of F is not equal to 0. Then probability of A union B when F has occurred is probability of A plus probability of B minus the intersection. And in particular, if A and B are disjoint event, nothing but mutually exclusive, then this element will be 0, this probability will be 0, and I'll get only the first two terms. We have to prove this. Let I erase this and then we will start the proof. Try to make it out. Okay. Now, dear students, let us move on to the proof of property number 2. So, as we are aware that S is a sample space and F is an event which is already occurred. You can see it's present below here, and A and B are the two events. Now, we have to just prove this result. So, coming to the proof of this, let us consider the left hand side probability of A union B when F has already occurred. Okay. Now coming to the result, what is probability of E when F has occurred is probability of E intersection F divided by probability of F, where probability of F is not equal to 0. Now you see carefully, we have to take intersection between the event yet to occur and already occur. So here it is A union B yet to occur. So it is probability of A union B intersection F whole divided by probability of F, where probability of F is never equal to 0. Now here I can think of applying distributive property. See carefully. See this. It is A intersection B. Sorry, A union B intersection F. Can't we apply distributive property? And we will have A intersection F. Okay. Union B intersection F. So using this distributive property, I can rewrite. So now applying this on here, just substitution. So we are going to have is equal to A union B intersection F is here. That is P as it is. I'll take a rectangle bracket to avoid confusion. So in place of this part which is there inside the bracket, this entire thing which is present here, I can substitute. It is A intersection F union B intersection F whole divided by probability of F. Now see the numerator. It is of the form P of A union B. Recall. That's what I recalled all the first PUC concept. What is probability of A union B? It is probability of A plus probability of B minus probability of A intersection B. Okay. So in place of A, we have this. This is our A. Union, union. In place of B, this entire thing is what? B. So now let us apply this formula here. So what we are going to get probability of A. What is A? A intersection F. Plus in place of B, B intersection F. Minus probability of intersection of what are present here. So intersection of both. What is that? A. Let us take a rectangle bracket to be clear. A intersection F intersection B intersection F whole divided by the denominator. Now see the thing what you want. You want F for all, nothing but if you obey this definition. So this denominator should be present for all. So this is dividing the entire. So we split probability of A intersection F divided by probability of F. Then plus probability of B intersection F divided by probability of F minus, see carefully, all are intersection, and we know that intersection of F with F is F itself. Intersection of same event will be the same event. So since all the intersection of this F and F will be only once we can write. So I am going to regroup all the intersection. So there's no problem in regrouping it. So A, this A, then intersection B, okay, and then intersection F. Whole divided by P of F. Now focus on the definition of conditional probability. Probability of E when F already occurred is probability of E intersection F divided by probability of F, where probability of F is not equal to 0. We are now going from right to left. That's what in mathematics you should know, left to right and right to left. See carefully. You should have intersection, and if the event which is already occurred, those are present, numerator and denominator, then it will be the event which has present only once, that is yet to occur, and the event which has already occurred, no, F, it is present twice. So just see carefully. Here also this goes exactly. F. Here also F. Here also F. Which is present only once? A. So this will be probability of A when F has occurred, plus here probability of B when F has occurred, minus probability of A intersection B when F has occurred. And don't forget the left hand side. This, let us substitute here, means write it here, the probability of A union B when F has occurred is this. P of A union B when F has occurred is P of A when F has occurred, plus P of B. I repeat, P of A union B when F has occurred is probability of A when F has occurred plus probability of B when F has occurred minus probability of A intersection B when F has occurred. That we have proved. Now, in particular, what we are saying is if A and B are disjoint event. When do we say disjoint event? Let us take this as 1. If A and B are mutually exclusive events. So when I say mutually exclusive events, what's the meaning of this mutually exclusive event? Two events are said to be mutually exclusive if they are disjoint, nothing but intersection should be empty. When intersection is empty, then the probability of A intersection B when F is occurring will be what? 0. Since there is no element, it's an impossible event and the probability will be what? 0. If I'm going to substitute this back in equation number 1, our equation number 1 will turn to probability of what? A union B when F has occurred is equal to probability of A when F has occurred plus probability of B when F has occurred minus this is 0. Anything separated by 0 is same thing, correct? No? So we have got even this result as well. Okay. Now let us move to the last property. First, kindly make a note of this. Yes, dear students. Now moving on with the last property, which says probability of E complement when F occurs is 1 minus probability of E when F has occurred. Coming to the proof of this, see, the first property which we proved was, recall, we know that probability of the sample space when F occurred is what? 1. Now I'm going to use this result where A and B are mutually exclusive events. See, if I take a diagram here with respect to only E, this is the sample space. If I've got event E here, where is E complement? I want E complement. E complement what? Not E, nothing but other than E. This entire region is what? E complement. So you can see very clearly that sample space is actually union of both E and E complement, and from diagrams very clear, see, E and E complement, entire thing is what? Rectangle box, that is sample space. And if I take the common between E and E complement, what I get? Empty. Disjoint even they are. So in place of sample space, we can write from here that it is union of E and E complement when F has occurred. And since E and E intersection is empty, nothing but they are mutually exclusive, nothing but they are disjoint, I can go with this. If A and B are mutually exclusive, union is equal to sum it is. So here union should be equal to sum, nothing but probability of E when F occurred plus probability of E complement when F occurred is equal to 1. And here I want only E complement when F occurs, so transpose this. We are going to have therefore probability of E complement when F occurred is 1 minus probability of E when F has already occurred. Yes. The same result we have in PUC, means I mean the first PUC, for simple event that probability of E complement is 1 minus probability of E. So same thing we can have. This is more general compared to this. Here only one particular event is occurring. Here one event has already occurred, that is F. And you can just see from here one more thing is always addition of E and its complement is always 1. Okay. So we have did all the concept. Now we are ready for question paper problem on conditional probability. Kindly make a note. Yes, dear students, now let us move on to the problems on conditional probability. We have got only 4 problems, all of each 1 mark. So for model question paper number 1, as you know, this is for the academic year 2025 to 2026. That's your academic year, and issued by KSEAB board. Now question says a 1 marker question, question number 20. If F be an event of a sample space S, then probability of S when F has already occurred, fill in the blanks question it is. See, this is from the property. As far as I said, properties are important. Let us again recall. See, recall what is conditional probability. Probability of E when F has already occurred is probability of E intersection F divided by probability of F, where probability of F should not be equal to 0. So in place of E we have S here, in place of F we have F only. So if I just apply the formula, we will have for this, okay, for this I am writing probability of S intersection F divided by probability of F. Since in the question S is given as sample space, so recall sample space is a rectangle box here and F is the subset of it. It's all the S is all the possible outcome of the given random experiment. F is a subset of this. So surely F, since it's a subset of S, F intersection S, nothing but the common between the rectangle box and the event F will be what? This one. This is the common event. So you will get what? F only. So having this logic, we can say that this will be what? Probability of F only. Probability of F by probability of F both will get cancelled and I will get equal to be what? 1. Therefore the value is what? 1. So yes, this value is 1. Let us move on to the next question from model question paper number 2. One marker question, question number 14, MCQ based. If probability of A is half, probability of B is equal to 0, then find the probability of B when A has occurred. Okay, so as we know, again coming to solution of this, probability of B when A has occurred, using this formula again, in place of E we have B and in place of F we have A, just substituting there. So we are going to have probability of B intersection A divided by probability of what? A. Take off the question. Yes, proceeding with this. See, probability of A. Okay, fine. This is even A is already occurred. Now the information is given here. Probability of A is half. So denominator is half. But they have said probability of B is 0. Nothing but this event has not occurred. It is impossible event. So when the event has not occurred, even the intersection will be what? 0. Because B has not occurred. 0 by half is what? 0. So option W is correct. I hope this is clear. Coming to model question paper number 3, a one marker question, question number 15. If probability of E is 0.6, probability of F is 0.3 and probability of common occurrence is 0.2, then probability of F when E has already occurred. Be careful here. In the formula we had E is yet to occur, F has already occurred. But here they are given E to be already occurred and F is yet to occur. So no change, mean to say logically no change. What the formula says, take the intersection of both and in the denominator here, whichever the event present below, that should be mentioned here, correct? So intersection of these two will be probability of F intersection E divided by which is the event already occurred, that is E. That should be there in denominator, where probability of E is not equal to 0. F intersection E or E intersection F, both are the same. We know from chapter 6, intersection is commutative. So whether this or this both are same, so the value is, this is what? 0.2 divided by probability of E is 0.6. After decimal we have only one number, after decimal only one number, so we can remove the decimal. Then what is remaining? 2 by 6. Simplify. 2 1s are 2 3s are. So answer is 1 by 3. 1 by 3 is in option C. So option Chalu is correct. Now let us move on to the same model question paper. One marker, fill in the blanks question. If A and B are two events such that A is subset of B. What they are saying? A is subset of B. Fine. A is subset of B. From this we came to know. And probability of A is not equal to 0, which says that it is not an impossible event. Then probability of B when A has occurred. Fine. Probability of B when A has occurred. Again, B is yet to occur and A has already occurred with this formula. So I'll be getting probability of B intersection A divided by probability of A, where probability of A is never equal to 0. In the question they have said A is subset of B. Again take a Venn diagram. It's the same scenario of this only. So let's have a logic here. But here they have not said B is a sample space. So if I say A is this, event A is this, then the event B is this. Okay. Now what they are saying, A is subset of B. So A is contained in B. I want common. Common between this circle and the entire circle is what? The one just contain nothing but what? Set A. So very clearly B intersection A is A itself. So I will get the numerator will be what? P of A divided by P of A. Both are same. So both will get cancelled, get 1. Therefore the answer is 1. Probability of B when A has occurred is 1. So this answer is 1. So all the questions from conditional probability are done. Kindly make a note. Now we'll take independent event concept. Kindly make a note. Okay. Dear students, having completed problems from conditional probability from model question paper, now let us move on to next concept, that is multiplication theorem. Multiplication theorem on probability. See, as I said before also, no, it's not of more of formulas, it's the ability to understand the question. And that's what you can see, no, in the word probability, see, ability to understand the question, ability to understand the concept, because we don't have too many formulas. Okay, recall once conditional probability, if E and F are the two events of the sample space S, then the conditional probability P of E when F has already occurred is probability of intersection of both of this common occurrence divided by probability of F, where probability of F should never be equal to 0. Only then conditional probability will hold good. Nothing but F should already occur. Now after cross multiplying here, we are going to have probability of E when F occur into probability of F is equal to probability of E intersection F. A is equal to B, same as B is equal to A. So if I write this one first, then we get probability of E intersection F is equal to probability of E when F occur into probability of F, where probability of F should never be equal to 0. This is one scenario. Next, here we took a case where F has already occurred and E is yet to occur. Now if I take a scenario that, this is first scenario. Now if I take the second scenario, probability of F when E has occurred, then what will be the formula now? Intersection of both, that is probability of F intersection E divided by probability of E, where probability of E should not be equal to 0, because E is already occurred, F is yet to occur. So surely this should be what? Not an impossible event. Now again having cross multiplied here, we are going to have probability of F when E has occurred into probability of E is equal to probability of F intersection E. Again A is equal to B, same as B is equal to A. I write this one first here. Probability of F intersection E is equal to probability of F when E has occurred into probability of E, where probability of E is not equal to 0. Now see both, let's give a comma here. This is our equation number 1, this is our equation number 2, and this is comma here. So if you see the left hand side is same, don't forget E intersection F and F intersection E both are same. So since E intersection F is same as F intersection E, I can say that left hand side is same. Since left hand is same, I can combine these two. Probability of E intersection F will be probability of here E when F has occurred Okay, or I write first this one order I will write, so that I can make you understand in general. So probability of F into probability of E when F has occurred. Just sign interest in the order A into B same as B into A, commutative. Provided probability of F is not equal to 0 and probability of this is also same as this. So again I write this one first. Probability of E into probability of F when E has occurred. So now this is our multiplication rule, and obviously probability of E should not be equal to 0 for second case is multiplication rule. Now from this we are going to have one generalization also. Let us suppose that in place of only two events, if I have got three events, that is E intersection F intersection G, then how we are going to write? That's what I said. No, I just changed the order from here to here. Let us see this. Whichever the event you write here, that is in denominator. Similarly here. So suppose we go with order 1 and 2. So if we go with this, okay, 1, I wrote first one. Then I write second one. No, see carefully. The one which you have already written, that's in denominator or already occurred. So similarly here, P of E if I write, then into, then what will happen? Probability of, next is F when E has occurred, into, now write G, probability of G when this two have occurred, E intersection F. Okay, so this will be our generalization, and we also denote, and we can also write this one as probability of E into probability of F when E has occurred into probability of G, and here together it is. So we also denote E intersection F as only EF. So here EF. So we can generalize like this for three events. Okay, for how many? 3 events. Like this we can generalize for n events. Okay, now let us try to understand whatever we denote. Now from here let us understand the definition of independent events. That's our next concept. Independent events. So two events E and F are said to be independent events if occurrence of one is not affected by occurrence of another. So both should not affect each other. Okay, that we call independent event. Now let us understand mathematically. If I talk with respect to conditional probability, probability of E when F has occurred. So in conditional probability, as we know that F has already occurred, and this is also going to calculate the occurrence of E. But now since we are saying that E and F are independent event, E and F are what? Independent event. Independent events. Now whatever we discussed till here, we have not said E and F to be what? Independent event. Now we are saying. Now since it is independent event, it means what? Occurrence of E should not be affected by occurrence of F. Therefore, should get back directly P of E only. And obviously, probability of F is not equal to 0. Similarly, if I talk about probability of F when E has occurred. So since again they are independent event, occurrence of F should not be affected by E. Therefore, I should have probability of F itself. So since I said it's not going to affect, so even though event E has already occurred, the occurrence of F is remained the same. It's not going to get affected by E. Similarly here, occurrence of E is not affected by F. You can see only probability of E here. So here probability of E, because it will already occur, that should not be equal to 0. First kindly make a note, and now we are going to have one generalized formula for independent events. Kindly make a note of this. So now dear students, continuing with the independent events, if I take this as equation number 3, because previously I have taken as 1 and 2. Now if I just substitute this in equation number 3, just see what equation number 3 becomes. Probability of E intersection F is equal to probability of F as it is. Now since it is an independent event, probability of E when F occur, probability of E when F occur is probability of E itself, where probability of F is not equal to 0. Similarly, if I go with the second line, so this both are value for probability of E and F, common occurrence. Again here probability of E into probability of F when E occur, recording no? Yeah. Probability of F when E occur. Probability of F when E occur is probability of F. And surely here probability of E should not be equal to 0. So combining this, we can just say that probability of E intersection F is probability of E. See, both are got same, no? P of F, P of E, same as P of E and P of F. Nothing but they are numbers. Numbers are commutative in nature, so I can add only once. This will be the condition for two events to be what? Independent. So whenever we have to check two events are to be independent, this will be the condition that common occurrence probability and individual occurrence probability both should be equal. This product should be equal to the intersection, and we denote E intersection F as EF. So this can be written as probability of E intersection F same as probability of EF, which is again same as probability of E into probability of F. Please don't think that P is multiplied to this and you got this. No, you can see I have derived that, and this is the notation for intersection. Okay, this is for two events. So this will be the condition. So this will be the definition for independent events. Okay, is definition for independent events. And as a note, I would like to say, let us suppose that this probability of EF is not equal to probability of E into probability of F, then E and F are not independent. When I say not independent, nothing but they are dependent events. So whenever it is not satisfying the equality, they are unequal, then it is dependent event. Now let us try to also generalize for three events. If A, B and C are independent events, then what should happen? Then probability of A intersection B, or as you know that even if I won't write intersections, understood, so henceforth I will not write. Probability of AB is equal to probability of A into probability of B. Okay, next probability of, I'll do one thing, I will write this one there. Okay, see carefully. Right on the top here. So again I'm repeating this last line. So three events, again here, no problem. Three events. So again I'm writing these two lines here. Nothing wrong, space not sufficient. So three events, recording no. Three events A, B and C are said to be independent events if probability of A intersection B, which is same as probability of AB, is same as their product. Probability of B intersection C, which is same as probability of BC, is again equal to their product. Probability of C intersection A is again same as probability of C A, again equal to their product. And lastly, probability of A intersection B intersection C, simultaneous occurrence of all the three, should be same as probability of A into probability of B into probability of C. Only then any two, for these three events to be independent event, all these four conditions should be satisfied. First pairwise, they should be independent, and lastly all together. Like this we can generalize for n number of events. So we have discussed about independent event. One last point I will take. First, you make a note of this. Okay, dear students, let us try to go for some concept here without any proof. Okay, this will be very useful for one marker. Who knows, for one marker they may ask. See, presently we are discussing about, for let I erase this. Presently we are discussing about independent events, and we have derived one condition also as a definition, and we have taken as a definition. So if, as a note we can have, if E and F are independent, these are two independent events, then what we can say, then first point, if E and F are independent, even E and F complement are also independent, are also independent events. Similarly, E complement and F are also independent events, and E complement and F complement are also what? Independent. So as soon as given that E and F is independent, all the other combination nothing but E complement F, and both are complement also independent. And one more point to be understood: if E and F are independent event, then probability of at least one of the event, nothing but A union B, will be equal to probability. Okay, let's write this result. Okay, see this very carefully. Let's take E and F only. So probability of E and F, nothing but at least one of the event should occur. So union, if I take, it is same as probability of E plus probability, this is F, okay, F minus probability of E intersection F. Now since it is independent event, we can say that it is the same as probability of E into probability of F. And here we have probability of E plus probability of F. Now, so continuing with this, if you see, probability of F is common. So probability of E is as it is, plus probability of F is common. Remaining will be 1 minus probability of E. Correct now? Here P of F is common, so P of F is out, so 1. Then here P of F is out, so P of E. What is probability 1 minus probability of E? It is probability of E complement. So we can just write, this is probability of E minus it. So we can write that probability of F, and this 1 minus P of E is probability of E complement. And for this also I can write as 1 minus probability of E complement. Just if I take transpose here and this one here, I'll get this. Correct? Now here, see what is come in this. So 1 minus, again in this P of E complement is common. So the remaining is minus, the minus will be plus. P of E complement is common, so plus 1. Minus plus is minus. P of E complement is common, so remaining is P of F. What is P of 1 minus P of F? It is P of F complement, and here P of E complement as it is 1 minus. So probability of at least one of the occurrence can also be found by this if E and F are what? Independent events. So with this we have completed all the concept. Now we can start with the problems. Kindly make a note. Okay, dear students, for a while, yeah, fine. Dear students, let us move on to the problems on independent events. One marker question from KSEAB model question paper of the academic year 2025 to 2026, nothing but your academic year. Question number 14 says, two cards are drawn at random and without replacement from a pack of 52 playing cards. Find the probability that both the cards are black. First, let us try to recall pack of cards chart there. So totally we are going to have 52, okay, playing cards or pack of cards. I write pack of cards only. Pack of cards totally 52. What is 52 by 2? 26. So we are going to have 26 black cards and 26 red cards. Again 26 by 2. We are going to have 13 spade cards and 13 club cards. Clubs, here spades. And here also 2 division coming to red, and here diamond. Again 13 diamonds, and then here hearts. 13 in number. Now what are those 13 cards? Those 13 cards are 2, 3, 4, 5, 6. Hope so recording. Yeah. 7, 8, 9, 10, then K. Okay, before, okay. Then Q, then A, and then J. Fine, I should write here first. No problem, no problem. So just see how many cards are there. 2 to 10 we have 9, then 10, 11, 12, 13. These 13 cards are there in each of these. What are these K, Q, A, and J? Where? K is king, Q is queen, A stands for ace card, and J stands for jack, not joker. Joker will be an additional card which is not present in 52 normal playing cards. So if you just analyze this, each of the card 2 to 10 and then K, Q, A, J is present in all these 4 divisions. And since there are 13 cards, 13 into 4 division will be 13 into 4 will be 52. Now if I talk about card 3, is present in spade also, clubs also, hearts also, and spades also, and diamond also. I mean to say spade, clubs, hearts, and diamonds. If I talk about the card king, present in all the 4. If I talk about club with number 4, clubs with number 4, only one card. I have specified the condition. I want card with number 4, and I should be club. Yeah. If I say I want red color card with number 5, red 5, there will be 2 cards, one in each, heart and diamonds. I hope this is clear. Now it is proceed with the problem. 2 cards are drawn at random and without replacement. What's the meaning of the word without replacement? First, let us understand this. When I say the word without replacement, imagine that you have got a box and you have got some balls, 5 balls I have got here. When I say with replacement, it means I will take out the ball, I will check the reading, whatever it is, and again I'm going to put it back. This we call with replacement. We are going to replace the object with replacement. So here the object remains the same in the bag. Whereas when I say without replacement, no. After I will take out the ball, whatever the balls we have, we are not going to put it back. We are not going to put it back. Once taken, is taken out. So here number of quantity will reduce. Okay. So they are saying without replacement, nothing, but again we are not going to put it back. This scenario is not there, so the quantity will change. And they are taking 2 cards from the pack of 52 playing cards. Find the probability that both the cards are black. So coming to the solution, B I will take for black cards. Now here probability of first ball to be black and second also black. Why is that twice black? They said 2 cards are taken and they are saying both the cards are what? Black. Okay. Now see, this is independent event. If I take the first card out and the second card out, occurrence of first card will not depend on the second card. Similarly, second card will not depend on first card. So it will be probability of B into probability of B as well. I know some also let B when B occurred. Again, since it is independent event, probability of B when B occurs what? Probability of B only. Now probability of B. So for the first time when I go for taking a card, I want recall what is probability of any event. It is favorable outcome divided by total outcome. So favorable outcome, how many black card do we have? 26. Out of favorable. Total cards are 52. And out of 26, one card is taken. Out of 52, one card is taken. Both are in here, both are black cards taken out. Now, since it is said without replacement, quantity should reduce. Which quantity? Black card quantity should reduce. So now in place of 26 black cards, I should have only 25 black cards. In place of 52 plain cards, I should have one card less because I have taken out, so 51 cards. So for the second will be 25 black card divided by total number of black cards. So here 26 ones are 26 twos are 1 into 25 will be 25. 2 into 1 is 2, 2 5s are 10. 25 by 102. 25 by 102, option C is correct. I hope this is clear. Now let us move on to 15th question. If A and B are two events such that probability of A is half, probability of A union B is 3 by 4, probability of B is Q, then the value of Q, I have to find this value Q. If A and B are mutually exclusive events, see, mutually exclusive event, as I discussed first PUC concept. Since they said mutually exclusive event, intersection between A and B should be empty. This implies probability of A intersection B should be 0 because there is no event there. Now they have given probability of A union B. So what is probability of A union B? The unit is 3 by 5. Recall the formula. Probability of A union B is probability of A plus probability of B is equal to 3 by 5 as it is. Let I continue here. Probability of A they are given half. Probability of B they are given as Q is equal to 3 by 5. Solve for Q. Sum of two terms I can transpose here. So Q is equal to 3 by 5 minus half. LCM of 5 and 2 is what? 10. 10 by 5 will be 2. 2 3s are 6 minus 10 by 2 will be 5. 5 1s are 5. So answer will be 1 divided by 10 will be Q value. So what is the value of Q here? 1 by 10. Option blue is correct. Okay, kindly make a note. Yes, dear students, let's move on to the next problem from model question paper number 1 and it's a 2-marker question on independent events. We are dealing with now independent events problems. A die is thrown. When I say a die is thrown, surely the outcome of that will be 1, 2, 3, 4, 5, 6. These are the possible outcomes. Since a die is thrown, let E be the event. E is the event. The number appearing E is a multiple of 3. So what is E? Multiple of 3. Which are the multiple of 3? 3 as well as 6. So I wrote the data. Next, F be the event that the number appearing is even. Among these, which are the even numbers? 2, 4, 6. F is the event. 2, 4, 6. That's what I said. No, ability to understand the question. Probability, ability to understand the question and apply the concept. Okay. Find whether E and F are independent. So we have to check are they independent or not. For that, recall two events are said to be independent if probability of E intersection F is same as probability of E into probability of F. If it is not equal, then it is not independent, nothing but it is dependent. So I have to find one by one. So let us find the E F, nothing but E intersection F. What's common between the both? 6 is common. So now let us find probability of E. What's the formula? Favorable outcome divided by total outcome. So what is probability of E here? 2 and S is 6. So 2 1s are 2 3s are. So probability of E is 1 by 3. Okay. Next, probability of F. So again, following the formula, whatever the event is the same event here. So favorable outcome of F divided by total outcome. In F we have 3 outcomes divided by S we have 6. So 3 1s are 3 2s are. Therefore, probability of F is 1 by 2. Let's multiply this probability of E into probability of F, that is 1 by 3 into 1 by 2 will be 1 1s are 1, 2 3s are 6. Let us keep this one as it is and let us highlight this. We also find intersection. Let us take it here. Probability of intersection we have to find. So probability of E intersection F is favorable outcome divided by total outcome. How many elements do we have in E intersection F? Only one outcome. Divided by sample space 6 outcome. Check, yeah. This is probability of E intersection what? F. So probability of E intersection F is 1 by 6. This I got from 1. Therefore, E and F are independent events. Independent events. They asked us to check whether it is independent or not. Yes, it is independent event. Now let us move on to model question paper number 2. A 1 marker question, 15 problem. 2 balls are drawn at random with replacement. In the last problem, I discussed about with replacement and without replacement. When they say with replacement, after whatever the balls or whatever the quantity, whatever the object we have got, we take out, we see the reading, whatever they are asking, and since they said with replacement, we are going to put it back, due to which the quantity will remain same. Okay. So they said with replacement from a box containing, what the box is containing? The box is containing 10 black and 8 red balls. Then the probability that both are red. Both are red. So probability that first ball also red, the second also red, where R stands for red here. And again, it's an independent event. I can just say it's the same as probability of R into probability of R. Some will also go like this. Other way of solving, probability of red and red will be probability of red into probability of red when red has occurred. It's an independent event. Again, this will be same as this one, the back. Both are same. Now, probability of red. How many balls do we have? Recall what is probability of any event A? It is favorable outcome divided by total outcome. So, number of favorable outcome. So, coming to red, how many balls do we have? 8. 8. Total outcome. Total, how many balls we have? 10 plus 8, 18. Into, before we go ahead, again check this. The entire solution depends on this. Since they said with replacement, quantity will remain same. Last time they said without replacement, due to which quantity reduce. I'm talking about pack of cards. Okay. In that problem, we had black card to be removed, right? 2 black cards. First it was 26 by 52. Next it was 25 by 51. Why? They said without replacement. Here it is with replacement. So how many red balls? Again it is 8 divided by what? Total. Correct? No, total how much? 18. Now simplify. 10 plus 8 is 18. Simplify. 2 4s are 8. 2 9s are 18. Again 2 4s are 8. 2 9s are 18. 4 into 4, 16. 9 9s are 81. 16 by 81. Option Bablu is correct. I hope this is clear. Recording, no? Kindly make a note. Okay, dear students, from model question paper number 2, a 1 marker question on the same concept, independent events. If probability of A is 3 by 5 and probability of B is 5 by 10 and A and B are independent events, then probability of A intersection B is 3 by K. What is K value? They are asking. As we are aware that for 2 events to be independent, probability of A intersection B should be equal to probability of A into probability of B. Probability of A intersection B is 3 by K. Let us substitute. Probability of A is 3 by 5 into probability of B is 5 by 10. Now very simple, 5 and 5 will get cancelled, 5 by 5 will get cancelled, and here 3 by 3 and 3 will get cancelled, get 1 by K is equal to 1 by 10, or cross multiply, K is equal to 10. So the value of k is what? 10. Very simple. Next, this was a fill in the blanks question. Question number 29 from the same model paper. It's a 2-marker question. Question says a dice toss thrice. This problem is going to make you understand the application of independent event. If you just see this first line, just read this: a die is tossed thrice. If I write the sample space for a die being tossed thrice, number of element in the sample space will be 6 power 3. Why 6? When a die is rolled once, outcomes are 6. And how many times it is tossed? 3 times. So we'll get 216 outcomes. Writing 216 outcomes and then finding the probability of getting an odd number at least once is very difficult. So we are not going to talk with respect to 3 dice. What we are going to do is we are going to apply independent event concept. One question will come, sir, how you can think of independent event here? It's not mentioned in the question. Yes, but when I have a 3 die, occurrence of first die will not depend on second die. Occurrence of second die will not depend on third die. Similarly, occurrence of third die will not depend on first die. Therefore, it is independent event. See, whether a die is tossed thrice is same as, see this again. I have got 3 dice, 1, 2, 3, and I am rolling. Once is same as rolling 1 die 3 times. Okay. Now, let us go for a problem. Solution will start from here. We are not going to take this approach as it will be too difficult and too lengthy. So in the solution, I'm saying very clearly, when a die is rolled, what? Once. Highlight point here is I am talking with respect to only 1 die, but in the question they have said thrice. Okay, now see how we are going to go about. When die is rolled only once, the sample space will be 1, 2, 3, 4, 5, 6. And the question is on getting an odd number at least once. I'll first focus on odd number. So if I say A is getting an odd number, which are the odd number do we have? Before we go ahead with this, no. First, now let us move on to what they want. What they want. Odd number at least once. What? Odd number at least once. Decode this. At least means greater than or equal to. How much? Once. I want odd number at least once. It means when the die is rolled, I'll be having triplet. Why triplets? There are 3 dice, no? So this is the outcome for the first die, this is for the second die, this is for the third die. Okay. So when they say at least once, it means out of the 3, 1 die should give odd number, or 2 die can give odd number, or all the 3 can give odd number. Okay, that's what at least greater than or equal to which number? 1. What we are going to say is the same as what is probability of event E. It is 1 minus probability of E complement. So I can say the same as 1 minus probability of, they said at least once I want odd number. I will say no odd number. No odd numbers. I have taken the complement. Whatever I want, I have denied. Whatever we have got E, that is denied. E complement is what? Denying, saying no, rejecting. So I don't want any odd number. So it means now A I have taken as getting an odd number, but I want no odd number. So A complement. So see this 1 minus probability of A is getting odd number. I am writing here A complement. This was the first die. For second die also I don't want an odd number. For third die also I don't want an odd number. So A complement is getting or no odd numbers. No odd numbers. Now probability of, first A complement, which are the numbers are not odd here. So 2, 4, 6 are not an odd number. So probability of A complement is number of favorable element, means outcomes in A complement divided by sample space. How do we have here? 3. So 3 divided by, totally here how much? 6. 3 by 6. Therefore probability of A complement will be 3 1s are 3 2s are nothing but half. This is half. Let us write greater or equal to bit more here. Nothing wrong, space was not there. Now Since it's an independent event, I can split 1 minus this probability of A complement into probability of A complement into probability of A complement, because it is independent event. So 1 minus probability of A complement is half. Again A comp is what? Half. Again here also half. I all got from equation number 1. So 1 minus 1 into 1 into 1 is 1. 2 into 2, 4, 4 2s are 8. LCM, there is nothing here 1. LCM of 1 and 8, 1 and 8 is 8. 8 by 1 is 8. 8 into 1 is 8. Minus 8 by 8 is 1. 1 into 1 is 1. 8 minus 1 is 7. 7 by 8 will be the probability of getting an odd number at least once. I hope this is clear. So this particular problem is giving you the application of independent event. Without writing the sample space containing 216 elements, we can get the answer directly. Okay, kindly make a note. Okay, dear students, we are with the last model question paper, that is 3, and after this we have got base theorem. That is a short 3-marker question. In all the 3 model papers, each model paper we have got 1 question from base theorem, which we will take after this. Question says, a 1-marker 14 question from model question paper number 3. Probability of solving a specific problem independently by A and B are half and 1 by 3. Solution. Let us write the data. Probability of solving by A is 1 by 2. Probability of B solving is 1 by 3. If both try to solve the problem, then the probability that exactly one of them solves the problem is exactly one of them should solve the problem. What's the meaning of it? See, if A is solving the problem, B should not solve. So B complement. Here this probability of B solving the problem, both A and B solving the problem, a specific problem is given. So here B and A solving probability is given. They said exactly one. Let us write that one again here. Probability that exactly one of them solves the problem. So here, let us suppose that if A is solving, there are only 2 people involved here, A and B. If A is solving, B should not solve, so B complement. Or if B is solving, A should not solve the problem. That's what exactly one of them. Both should not solve the problem. Any one should surely solve, exactly one. So or means addition. So probability of A into B complement, probability of A B complement into probability of A complement into B. And I give a concept that, okay, all means plus here, and I already gave you a concept that if A and B are 2, if E and F are 2 independent event, even the complement is also independent event. So here this will be independent event. Here it will be probability of A into probability of B complement, plus this will be probability of A complement into probability of B. Now recall how to find complement of each. Probability of A complement is 1 minus probability of A. So 1 minus probability of A is 1 by 2. So 1 by 2, 1 minus half is half. So probability of A complement is half. Similarly, I want probability of B complement. Probability of B complement is 1 minus probability of B. So 1 minus probability of B is what? 1 by 3. So what is 1 minus 1 by 3? 2 by 3 after taking LCM. Substitute here. Probability of A is half. Probability of B complement is 2 by 3. Plus probability of A complement is half. Probability of B is 1 by 3. Now simplify. 2 into 3, 6. 2 ones are 2. 2 divided by 6. Plus 1 ones are 1. 2 threes are 6. So this is 6 actually. LCM of 6 and 6 is 6. So 6 here. 6 by 6 is 1. 1 into 2 is 2. 6 by 6 is 1. 1 into 1 is 1. 2 plus 1 is 3. 3 by 6. So 3 ones are, 3 twos are. So answer is half. So the option 3 ones are, 3 twos are, half should be the answer. 3 twos are 6 2. Yes, dear students, we got the value to be half, and I just took the paper. I have copied it wrong. This is not 3 by 2, it is 1 by 2. Option D is correct. Okay. Oh, forever I wear the headset. Yeah, fine. Just give me a second. Fine. Now let's move on to the question number 29, 2-marker question. Same like the previous 2-marker question. Okay, so all the 2-marker questions are on independent event. Question says an urn, there's a box, contains 10 black balls, 10 black balls and 5 white balls. 10 black and 5 white balls. 2 balls are drawn. How many balls? 2 balls are drawn out, one after the other, without replacement. Nothing but we should not put it back. This is not allowed. Putting back is not allowed. What is the probability that both drawn balls are black? Fine. Previously I think we had on red, it was with replacement. Here it is without replacement. Probability that both the balls are black. Okay, so B stands for black ball. Now again it's independent event, so probability of black into probability of black. Other way also write probability of black into probability of black when black has, the first ball is black taken out. Then also same, because it is independent event. Now how we can say, because drawing of the first ball will not depend on the second ball. Okay, whatever we draw, similarly second ball to first ball, it will not depend on each other. Probability of any event, recall. Probability of any event is favorable outcome divided by total outcome. What is the favorable outcome? Number of black balls 10. Total outcome 10 plus 5 15 into, since they said the what without replacement, I think, but again I'm not going to put it back. So the second rail, number of black balls, which was 10 in number, now since one is taken out, 9 black balls are pending, and total balls were 15, out of which one is already taken out, so remaining are 14 balls remaining. Now simplify. 5 2s are 10, 5 3s are 15, 3 1s are 3 3s are 2 1s are 2 7s are, so answer will be 3 by 7. This will be probability of withdrawing the black balls. So with this independent events, all the problems completed. Kindly make a note. Yes, students, we are ready with the last concept, that is chapter C. That is on Bayes theorem. But before we take Bayes theorem, we have to understand some of the basic things. Now first one is partition of a sample space. Partition of a sample space. We are going to divide the sample space. Let's consider and understand with the help of this diagram. Sample space, yes, is there, and this rectangle bracket stands for sample space, where sample space is all the possible outcome of a given random experiment. Now here let us suppose I have got one event E1, one more event is there E2, one more event is there E3. Like that I have so many events. It goes on, and somewhere I have got a last event En. Now just see the diagram, what we can see from the diagram. The first point, if you see E1, E2, there is nothing common. E2, E3, no common. E3, E4, even E2, E4, E1, E4, nothing is common. Pairwise they are disjoint. So EI intersection EJ is empty whenever I is not equal to J. For two different events, if we talk about, they are always what? Mutually disjoint. So nothing but that is all. Okay, E1, E2 up to E1 are mutually exclusive events. Mutually exclusive events. Second point. Union of all these are equal to sample space, nothing but E1 union E2. You can see in the diagram. If I take union of all these events, E1, E2, E3 up to all, I'll get sample space, nothing but all the events E1, E2 up to En are exhaustive events. Exhaustive events. Okay. Lastly, one more thing is all this probability should be non-zero, nothing but the event should occur. It should not be the case of we had not showed event and impossible. It should not be an impossible event. Event should occur. So these three conditions should be satisfied. Only then we say it is a partition. So the events E1, set of events E1, E2, E3 up to En is said to form a partition of a sample space if these three conditions satisfies that mutually they are exclusive, nothing but mutually disjoint. If I take pairwise, they are never going to have anything common, nothing is common. Then if I take union of all the events, I'll get sample space and probability of that any event. If I talk about I is equal to 1, 2 up to n, or for all I 1 to n, it should be what the probability should occur. It should be non-zero. This is about partition of sample space. Okay. Now we are going to go ahead with one of the result. After that, we are going to go for base theorem. So I'm going to erase this. Just kindly make a note of this. Okay. And obviously, when I say here, I and j are equal to 1, 2, 3 up to n for all the events should happen. Okay. But I should not take the both same event. Same event, if I take intersection, I'll get surely but non-empty only. Okay. Okay, dear students, now let us move on to theorem of total probability, and this will be a base to derive the base result. Okay. Now what this says, and understand this theorem carefully. This and the base theorem together will help us to solve the 3-marker question which is there in all the 3 model question papers. So theorem of total probability says let a set of E1, E2 up to En be a partition of a sample space. That's why I discussed what is sample space. Let's again go ahead here. Let's recall that. So let's write graph diagram for partition. Let us suppose that I have got a sample space yes, and I have got n events. Let us suppose event E1. Then here I have got event E2, E2 here. Then I have got event E3. Like this, we have got event E4. Then event E5. Okay, we have many events like this proceeding here and there, and ultimately somewhere after let's suppose here event E6, like this we are moving up to, ultimately we got somewhere an event En. Okay, we have got so many events, and if you see pairwise they are disjoint. E1, E2 there's nothing common, E2, E3 there's nothing common, E1 and E3 there's nothing common, E3, E4 nothing common, E1, E4, if I take any 2 pair, it is disjoint. So that's what we are saying, that coming to partition sample space, partition of the sample space, let's suppose that each of the event has non-zero probability of occurrence. We have 3 conditions for partition of sample space. The first condition for partition of sample space, yes, the first condition, as you remember, that the intersection between the 2 events, a pair event, should be always disjoint. This is true for all I comma j moving from 1 to 3 up to n. And if I take the union of all this, I should get back a sample space. So E1 union E2 union E3 union of all these events, if I take, I should get sample space, and probability of all of these events should be positive. This should happen for all the events I running from 1, 2, 3 up to n. All should occur. That's most important. Then what's going to happen? So see, till here it's the same thing what we have already discussed. Now we are having some additional thing. What? Let A be any event associated with S. With S, this sample space, there's one more event apart from E1 to En, and let us give in the diagram form in blue color marker. I'm just highlighting. Just see, this is our event E1, and this event E1 I'm writing here. This A is for the entire blue color, whatever the figure I have drawn, that represents event A. The occurrence of A, you see, it is such a way that it is having common with E1, E2, E3, E4, so E6. Purposefully I have given, no, it may not have common with some event, no problem. But at least with some it is having common. Okay. So it is again an event of sample space only. Then we have to show that probability of A. Because I want to know what is the probability of A. It is given by probability of E1 where into probability of A when E1 has occurred plus probability of E2 when probability of A when E2 has occurred plus dot 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 probability of En when probability of En into probability of A when En has occurred. In short, we wrote summation. So summation y, you can see plus 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 and P of E1. So Ej. See whatever index is the same index here. 2 2 n and here 1 1. So Jj and A. So J running from 1 to n. When J is equal to 1, we'll get this summation says plus J is equal to 2 plus J equal to 3 up to n. First, let us try to understand what's happening here. See, so far we had only one box given to us, only one urn given to us, and we have to find what is the probability of black ball, red ball, etc. Now comes more than one box, and we have to find the probability of getting a red ball, and red ball may be then both the boxes. I will be getting my point. So in place of only one box, now we have got more than one box. And here also we may have a red ball, and here also we may have red ball along with some black ball, blue ball, etc. Now I want to find the probability of red. Now that is in the both. That's why you can see probability of, if I say A is getting a red ball, it is in all the what events. Okay, so we have to find. So it is now not just one urn, it is more than one urn. Now how to go about? See carefully the proof. So first I mentioned the data here. Now from the diagram, one thing is very clear, that A is actually intersection of the sample space. A is same as intersection of itself with the sample space. But what is sample space? Don't forget, sample space is union of all the events E1 to En, E1 to En. So let us mention A intersection E1 union E2 union E3 union dot 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 union En. Now this event A intersection is taken with all, nothing but we are distributing it, applying distributive property. What it says, what is A intersection B union C? It is A intersection B union, and this is C, A intersection C. So we are taking union, means distributive property applying. So here you see we had only two events. Here we have n number of events. It will be done for all. So A with E1. So A intersection E1, then union as it is. So you can see now A intersection B, then union as it is, then A intersection C. So union as it is here. Then again this A is taken with the E2. We are distributing them. So A intersection E2. What we are trying to do, just see carefully. Then again A intersection E3, like this it will go. Ultimately union A intersection En, A intersection En. So what we have did, we have tried to find the common with each and every event with the A. Now understand, see the diagram. From the diagram it's very clear. Now for example E1 and A, here this part is E1 and A. This part is E2 and event A. This part is only this part is E3 and event A. You just see these three itself. They are again mutually exclusive event. There is nothing common between them. Again here also. So there is nothing common. This with this nothing, but they are mutually exclusive. So let I mention that this also implies that A intersection EI is empty for all I running from 1, 2, 3 up to n. If at all it's a mutually exclusive event, recall probability of A union B is probability of A plus probability of B, provided A intersection B is empty. So union is equal to sum. Union of two terms, so in union of two events, so it will be sum of two events. So here if I take probability on both the sides, probability of A is equal to probability of, I'll take a rectangle bracket, A intersection E1 union A intersection E2 union A intersection E3 union dot 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 A intersection En. Okay. Now let us understand this. See carefully this line. If they are mutually, if two events are mutually exclusive events, then probability of union of those two events is sum of those probabilities of those events. Now here we have got n number of events which are mutually exclusive. Therefore, the union will be equal to what? Sum of those probabilities. So this will be probability of A intersection E1 plus probability of A intersection E2. Hope this recording. Then plus probability of A intersection E3 plus dot dot dot. Last one, probability of A intersection En. Okay. Now, since by using multiplication theorem now, listen carefully what it said. Probability of E intersection F is same as probability of E into probability of E when F occurred. Sorry, probability of F when E occurred. Okay. So having this same logic we are going to have now. See carefully. Coming to this, probability of this one, I can write as probability of E1 into probability of A when E1 is occurring. Okay, for this. Similarly for this, what? So I have taken the role of E to be E1 and for F it is A. Okay. Then for this also, probability of E2 into probability of A when E2 is occurred. Then for this, probability of E3 into probability of A when E3 has occurred, plus moves on, and comes this probability of En into probability of A when En has occurred. So now I can write in short probability of A. If I want to find probability of A, I have to find in each of this probability, and in short we can write summation j running from 1 to n probability of Ej into probability of A when the event J has occurred. So this will be our theorem of total probability. That's what they asked. Okay, I hope this is clear. Now let us move on to base theorem. Kindly make a note. So here also what we are understanding is, if I want to find probability of getting a red ball, I have to find probability of red ball in the first box also, second box also, and whatever number of boxes are given. And A is what? Getting a red ball. So you can see event A is what? Common event to all. Okay, common event to all. Kindly make a note. Okay, dear students, now let us move on to base theorem. Now see, there is one apostrophe here. Usually we write before S, but here it is after S because the name of the person is base who introduced this. So it is, I said Naseer's, correct? No, for example, mine Math Universe with Dr. Naseer Ahmed is of whose? It is Naseer's. So I'll give an apostrophe here. S. It belongs to Naseer. Similarly, for base theorem, it belongs to base, but since the last letter of the person base is yes, what it is? Yes. So we write apostrophe here. So it belongs to the person base. Okay, fine. Just a small information with respect to language, English language. Now let us proceed. Theorem says if we have E1, E2, En are n non-empty events, non-empty events which constitute a partition of sample space. As soon as we say partition of a sample space, don't forget all the events should be disjoint. Union of that should be sample space, and probability of the occurrence should be non-zero. That's what they have given here again. That it is pairwise disjoint, then union should be sample space, and A is any non-zero probability. A is the one event common to all. Now, actually, what's happening? What we are trying to do? As I said before, also that we have been having more than one ball, and I want to know. I have got some red ball here, black ball here. Again, here have some red ball and black ball. Let us suppose let us write it a bit more neatly. I've got here 10 red ball and 5 black balls in first bag. In second bag, I might have 3 red ball and 7 black balls. Now, this theorem was saying what is the probability for say drawing of 2 red balls. It can be either from here or from here. This is giving sum of all those probability from each of the box or the bag. But now what Bayes' theorem is saying? Bayes' theorem is saying so far we used to have a box, independent event, first PUC, then conditional probability also. We used to have one box, and I used to draw a ball from a box. What is the probability that this ball is red, blue, green? Similarly, pack of cards. We have drawn pack of cards. What is the probability that this is a black card, etc. So we are behind of the object, not behind of the box. Now Bayes' theorem is ulta. Now we are drawing a ball. What is the probability that it has been drawn from the first bag, first box, or the second box? This we call reverse probability. In place of concern with the ball, I mean to say in place of concerned with the ball or the objects, now we are concerned with which box we have drawn the ball. That's what Bayes' theorem is all about. Now let us try to prove this. Coming to the proof, I have purposefully not erased this because we are going to just directly use this in the result. Probability, you can see it's a conditional probability, it's an extension of conditional probability. We can say the probability of EI when A has occurred. Again, I'm not writing the same thing here. Okay, it's understood that again we have to recopy something, but it's not a derivation for 3 marks. But as I said, you should know the concept. So, coming to conditional probability, what was the definition? Probability of E when F has occurred is probability of E intersection F divided by probability of F, where probability of F should not be equal to 0. So having the same intersection of this probability of EI intersection A divided by probability of A. Now by using multiplication rule, we can rewrite this one to be probability of EI into probability of A when EI has occurred. Why? By multiplication rule. Okay, divided by probability of A. Recall what was multiplication rule. Among this one you take as already occurred, that is EI. The whatever has been taken, no, when I conditional probability, this should go to denominator. Okay, mean to say already occurred. Now what is P of A? P of A already we have derived in total theorem of total probability. Just I'm going to substitute there. We are going to have probability of EI when A occurred is probability of EI into probability of A when EI has occurred divided by P of A. P of A is this summation of j running from 1 to n probability of EJ and A when EJ occurred. Probability of EJ into probability of A when EJ has occurred. And this is for all I is equal to 1, 2, 3 for all the events. This will be the result. And on this we are going to have a 3-marker question on Bayes theorem. So as I said, in this we are going to find what is the probability from which box we have drawn an object. Okay, and we are going to have more than one box. Kindly make a note. So yes, dear students, we are with model question paper number 1 issued by KSEAB. Okay, for the academic year 2025-2026, and Bayes theorem problem. We are taking a 3-marker question. Sure, one question will be there on Bayes theorem. Question says, before I go to the question, first, as I know, many students have a problem with Bayes theorem, how to solve the problem. So my suggestion is, first write down the Bayes theorem formula. So by Bayes theorem, I have purposefully left the space for the data here. Now Bayes theorem says probability of event EI when A has occurred is. How to remember the formula, that also will explain you. See, probability of EI into probability of A when EI has occurred divided by summation. Let I complete writing the formula, then I will explain you how are you going to memorize it. And this is for I is equal to 1, 2, 3 up to n even. See carefully. Probability of EI when A has occurred. Whatever you have got, take reciprocal of that. See, and EI as it is. The one which is below, that should be here. Whatever is there, same thing here, but in place of I, the index is J, because we have to run for all the events sum. Now, just see the way I am going to go ahead. Question says there are 2 boxes, namely box 1 and box 2. Box 1 contains, solution coming to box 1. Box 1 contains 3 red and 6 black balls. 3 red and 6 black balls. Back 2 box 2 contains 5 red and 5 black balls. 5 red and 5 black balls. One of the 2 boxes are set. There should not be this one there. This is a printing error. See, you see yourself. One of the 2 boxes, one selected. No, one of the boxes selected at random, and a ball is drawn. So among this, one is selected and a ball is drawn from the box which is found to be red. So whether I draw from here or if I draw from here, the drawn ball is red and red is there in both the box. That's what I was saying. So far we had a probability that if one particular box is given and has got some object like 5 red ball and 5 black ball, one ball is taken out. What is the probability? It is a red ball, black ball. But now it's more than one box and one ball is drawn, it's found to be red. What is the probability that it is drawn from? Find the probability that the red ball comes out from the box 2. So I'm bothered about this. So I want bothered about from which box we have taken. So E1, let be probability. E1 let it be selection of bag of box they have said. Fine. Box 1. E2 be selection of box 2. Now, before writing the data, first let us have the formula for our given problem. For that, read the last line. Find the probability that the red ball comes from box 2. So I want the probability of what? Red ball taken. Okay. And whatever we want, the common event. See, a ball is drawn, is found to be what? Red. Red is in both. So event A is drawn ball is red. Drawn ball is red. So drawn ball red is A. And I want it from which box? Second box. Second box is E2. So probability of E2 when A has occurred. This I have to find. Now go to the formula. In place of I, what do we have? N. So put I is equal to N. I mean, say put I is equal to 2. I mean, say put I is equal to 2. Then what we are going to have? Probability of E2 when A occurred is equal to, and I is to put I equal to 2 here. Probability of E2 into probability of A when E2 has occurred divided by N stand for number of disjoint event, and we have only 2 disjoint event, that is solution of first box and second box. So N is equal to 2 in this case. N is equal to 2. So when J is equal to 1, we will get probability of E1 into probability of A when E1 has occurred plus probability of E2 into probability of A when E2 has occurred. Now, since you have to find this, as and how you read the question, get all the data. Now see here, P of E2, P of E1 and all this should be known. What is P of E1? First, recall what is probability of any event. Probability of any event is favorable outcome divided by total outcome. So probability of E1, I think the selection of box. First box, we have only one box. So 1 divided by total. Total box are 2. So 1 by 2. Similarly, probability of E2 also. Because we have only one box with the number box 2. Total number of box. Okay, divided by total number of box. So as soon we have found P of E1 and E2, we have found P of E1 and E2. E2 is here, E1 is here, and it's also done. When you write like this, so you know what are the things to be found. Next what you want? This probability of A when E1 occurred. Understand here. E1, what? Box 1. And I want A. What is A? Red ball. Go to box 1. How many red ball? See, probability is what? Favorable divided by total. In the box 1, how many red ball? 3. Total ball 3 plus 6, 9. Don't divide them. Don't divide. See very carefully. Probability of, see, I have got this. Now I want to find probability of A when E2 occurred. So probability of A when E2 occurred. So E2 is what? Box 2. And what is A? Getting or drawing number of red balls. Go to E2. How many red balls you have got? 5. Totally 10 balls. So 5 by 10. Again, don't simplify. Keep as it is. You will see an advantage. Okay, now let us substitute. Probability of E2 and E1, it is half. Probability of E2 is half. Probability of A when E2 occurs is 5 by 10. Okay, in this case, no. What I thought is not happening. So you can cancel here itself. 3 1s are, 3 3s are. Usually, students want to simplify because we used to get such a number. No, where numerator denominator behind same factor, you can cancel at once. But this problem is not framed like that. What was there in the NCERT text, the remaining problem. Probability of A when E2 occurs is half. So I can substitute here half. And see carefully, whatever we have got, same thing is here. I can directly substitute without any second thought. This is same as this. Then plus sign here. Probability of E1 is half. Probability of A when E1 occurs is 1 by 3. Without any difficulty, I hope all of you agree, 1/2 will get cancelled everywhere. Now remaining is half divided by 1 by 3 plus this half. Half as it is. For the denominator, since plus is the LCM. LCM of 3 and 2 is 6. 6 divided by 3 is 2. 1 into 2 is 2. 6 divided by 2 is 3. 3 1s are 3. And this 6 will jump up now. So we are going to have 6 into 1 is 6 divided by 2 into 2 plus 3 is 5. 2 1s are, 2 3s are. So answer will be 3 by 5. So probability of drawing the red ball from the second box is 3 by 5. So it's a 3-marker sure question. Just always try to write the formula. Then last time you see what they have asked you find. As per that, give the index, make the formula ready, and from here you come to know what are the things you require from the question. Okay, kindly make a note. Dear students, now let us move on to model question paper number 2. Again, a 3-marker question from base theorem. Question says, okay, let I erase this. First, let I erase this so that we again understand how to frame the things. Okay. Statement again I've written. Yeah, it takes a bit time to copy down the question. Solution for this problem. Question says, of the students in a college, so there is a college, one college, it is known that 60% reside in hostel and 40% are day scholars not residing in the hostel. So when I say day scholar, those set of students who are not residing in the hostel. Fine. Previous year results reports that 30% of all students who reside in hostel attain A grade and 20% of 20% of day scholar attain A grade in their annual examination. So the common thing is what here? Attaining grade A. At the end of the year, one of the students is chosen at random from the college and he has an A grade. What is the probability that the student is a hostel? Okay, from hostel. So what is the probability that the student is from the hostel? So here in our college we have got two set of students. One set of student is day scholar, nothing but not residing in the hostel, and other set of student is residing in the hostel. But in this, the common thing is the student is selected and the student has got grade A in the examination. So see here. First, let us say that no, even student residing in hostel, E2, disjoint even, no, student reside, no problem, reside completely, student not residing in hostel. When I say not residing in hostel, we mean to say day scholar. Day scholar. Day scholar, when I say those set of students who go to college and come back home, those are called day scholar. But there are some students who come from a very long distance, maybe some other district, or to long distance to travel every day from home to college, and college to home back. So they go for a hostel, right? That's we call hosteler. Now they are saying a student is chosen and the student has got a grade A. Now if you see, let it be from the 30% student residing in hostel gets a grade A and 20% day scholar also get a grade A. So what is event A? Student with grade A. With grade A. And this A and this A are different. This A is as per the concept that event A is common to all the disjoint event, and this is grade A. Okay. Now what you want to find, understand, what is the probability that the student is a hostel, from the hostel. So probability of hostel, student residing in the hostel is E1. So probability of E1 such that student got a grade A. Student got a grade A. So I want to find this. So again, go back to formula. I said first write the formula here so that you understand what are the things you have to list out. In place of I, we have 1. So put I is equal to 1 in equation number 1. So when I put I is equal to 1, so probability of E1 when A occurred is probability of E1 into probability of A when E1 occurred divided by, don't forget, number of two disjoint events are only 2. Number of disjoint events are only 2. So n is equal to 2. N is equal to 2. So 1 by 1. When j is equal to 1, put j is equal to 1. Probability of E of 1 into probability of A when E1 occurred, plus summation means addition, plus j is equal to 2. Probability of E2 into probability of A when E2 has occurred. So these are the things we have to find one by one. Probability of E1. What is probability of E1? Before I go ahead, see the data whichever is given, no, it is in the form of percentage, and again here also percentage. Whenever data is given in terms of percentage, it's already in probability. Sir, how, sir? Come to this formula. What is probability of any event? Probability of any event, as you can see, It is favorable outcome, that is n of a divided by total outcome. Favorable outcome divided by total outcome. How are we going to calculate the percentage? For example, percentage of your marks. When we say 60%, how are we going to calculate? It is marks obtained divided by, I repeat, marks obtained divided by total marks. Marks obtained, nothing but favorable outcome, divided by total marks into 100. So whenever we get any information in terms of percentage, it's already in terms of probability. I hope this point is clear. Now they said E1 is residing in the hostel. So see, in the question, probability 60% reside in hostel. So they have given themselves 60%. 60% is same as 60 by 100. Let us not simplify anything. Let us retain P of E1. Yeah, I got this one also and this one also. Next, probability of E2 also I want. E2 is what? 40% day scholar. What is E2? Student not residing in hostel, therefore day scholar. Yeah, it is 40%. So probability of E2 is 40%, which is 40 by 100. Next, probability of A when E1 occur, nothing but student or E1 is what? Not E1 is what? Residing in hostel. Student residing in the hostel and getting grade A. Just check it out. Previous year results report that 30% of all students who reside in hostel attains grade A. So probability of getting grade A provided students are from hostel is 30%, which is 30 by 100. Then what next? So we got this. When we got this, we have got this also. Now probability of A when E2 occur, nothing but probability of attaining grade A provided student or day scholar. For 20% of day scholar attains grade A. So 20%. So all the information, whatever is given, we have collected. Now the time is only to substitute and get the answer. So probability of E1, it is 60 by 100 into probability of A when E1 occur, it is 30 by 100 whole divided by whatever we have got, same term we have got, so you can substitute the same. So 60 by 100 into 30 by 100 plus probability of E2. Probability of E2, yeah, here it is 40 by 100 into probability of A when E2 occur. Probability of A when E2 occurs 20 by 100. So all the information we have substituted. Now why I didn't ask you to simplify here, just see in base theorem now, since all are in ratio, see this by 100 will cancel here. Okay, so how we can cancel this? We have plus, we are taking common, 1 by 100 common here, so it will get cancelled with this, and here is into, so you cannot take common. So now this by 100 will cancel with this. Again, how? Take this 1 by 100 common, will cancel with this. Similarly, this 1 0 will cancel with this. Then this other 0 will get cancelled with this. So ultimately we are left with what are the things? See carefully. 6 into 3 divided by 6 into 3 plus 4 into 2. 6 3s are 18. Again 6 3s are 18. 4 2s are 8. 8 8 16. So I'll get plus 1 26. Simplify. This is very simple calculation. 2 9s are 18. Then here 2 1s are 2 3s are 6. So we are getting 9 by 13. This is probability of E1 when A occur. Nothing but student getting grade A provided. If they are hostel, no, student residing in hostel getting grade A is 9 by 13. Now let us suppose, no, in hurry you did for, let us suppose, for residing in, not residing in hostel, nothing but day scholar, and then you realize question was for hostel. No problem, whatever the answer you will get, no. For example, probability of E2 when A has occurred, surely you will get that time 2 by 13. Sir, how come without calculation you said you get experience? No, don't forget, we have always one property, probability of E1 when A occur is same as 1 minus probability of E1 when A occurred. Okay, complement I'll take. Complement. So already we discussed in conditional probability that for complement this is true. And since we have only two events here, E1 and E2, E1 is residing in hostel. E2 is not residing in hostel, nothing but they are complement of each other. So even if I found the other way around, I can just subtract that whatever I've got from this, I'll get the answer. So just by seeing this, I said 2 by 13, not 2 by 13, 10, 11, 12, 3 by 13 I mean to say, not 2 by 13, 3 by 13. Okay, fine. So if I find day scholar getting grade A, I should get 3 by 13. How I came to say, how can I say that? If I add that number to this, I should get 1. Because both are complement using this logic. Okay, fine. Kindly make a note. Okay, fine. Dear students, we are with the last problem. Okay, let I erase this so that we understand how we are going to write the formula. Okay. So as I said, always write the general formula. That is the base theorem formula. And from this, always we can get our particular formula. Now see, question says, given 3 identical boxes 1, 2, 3, 1, 2 and 3, each containing 2 coins. Okay, let's have in solution side over here box 1, box 2 and box 3. It contains 2 coins. Box 1, yeah, box 1 contains 2 gold coins. Okay, 2 G for gold will take. Okay, whereas in box 2 both are 2 silver coins. So 2 silver coins. And in the box 3 there is 1 gold and 1 silver coin. So 1 gold and 1 silver coin. So in each of these boxes there are 2 coins. First box contains 2 gold, second box contains 2 silver, and third contains 1 gold and 1 silver. Fine. A person chooses a box at random and takes out a coin. So from this one box selected at random, and person takes a coin out. And if the coin is of gold, what is the probability that the other coin in the box is also gold? First coin which he has taken is a gold. What is the probability that it's again what? Second coin is also a gold. Nothing but they're talking about probability of the coin drawn from the first box. So first coming to the solution, let us define the event. We have this time 3 events. E1, selection of box 1. E2, selection of box, like full this one, box 2. E3, selection of box 3. Now the common thing is when they have drawn, it is a gold coin. So drawn coin is a gold coin. Drawn coin is a gold. Yeah, continuing with this. Now what we have to find? What is the probability that the other coin in the box is also gold? Nothing but probability of the first bag. Because only in the first bag we have got 2 gold coins. Here there is no gold coin, and here already 1 gold coin is taken. Correct now? So this can't be the required box to be formed. So probability of even. Now in place of I, here we have 1. So in place of I, 1. Yeah, fine. But how many events do we have disjoint? 1, 2, 3. N is equal to 3. We have this time 3 events. Now let us substitute in place of I1 here. So probability in place of I1, probability of E1 into probability of A when E1 occur divided by when this is J. When J is equal to 1, probability of E1 into probability of A when E1 occur. This symbol stands for addition, so plus. Then put J is equal to 2, probability of E2 into probability of A when E2 occurs, then plus 5 plus summation up to 3 we have to go. So probability of, put J is equal to 3, probability of E3 into probability of A when E3 occurs. Okay. So we have to find all this one by one. Let us proceed. Now probability of E1. Probability of E1, we have 3 boxes. So selection of probability of E1 will be 1 by 3. Why? We have only one box and out of 3 we have to take. So favorable by total outcome. Similarly, probability of E2 is also same because we have only one box with the number 2 and divided by total number of box. And lastly, probability of E3 as well. So we have found probability of E1 here, P of E2 and P of E3. Now you want probability of A when E1 occur. Before I go ahead, kindly recall once again what is the formula to find probability of any event. It is favorable outcome divided by total outcome. That's what first PUC is so important to recall. Now see carefully. Probability of A when E1 occur. What is here? Drawn coin is gold. And E1 is first back. Come, go to first back. So here I want what? Probability of, see carefully, probability of A from E1. So I want gold coins. How many gold coins do we have? 2. Favorable outcome divided by total outcome. How many gold coins? 2. And how many total coins? 2. 2 by 2, 1. Next, so I've got this one. Now I want probability of A when E2 occurs. Probability of A when E2 occurs. E2, nothing but second box. E2 is selection of second box. Yeah. And I want what? Gold. How many gold coins we have? 0. Divided by total coins is 2. 0 by 2 is 0. So this is also done. Now probability of A when E3 occurs. Probability of A when E3 occurs. What is E3? Selection of third box. Yeah, third box is here. In that, favorable by total. A stands for gold coin. How many gold coins do we have? 1. Divided by total coins are 1 plus 1, 2. So we have got all the information. Now substitute. Probability of E1 is 1 by 3 into probability of A when E1 occur is 1. And whatever we have in numerator, the same thing is there here. Just substitute. Then plus probability of E2. E2, yes, where it is? It's here, no? 1 by 3. And probability of A when E2 occurs is 0. Then probability of E3. E3 is again 1 by 3. And probability of A when E3 occurs is half. Now just simplification. You can see very clearly anyway. 1 by 3 into 0 is 0. And here 1 by 3 and this 1 by 3 will get cancelled with this. So I can say 1 by 3 is common here. So remaining will be, I hope it's recording. Yes. Remaining will be 1 divided by 1 into 1 will be 1 plus, this is anyway 0 plus this is half. 1 plus half will be 3 by 2. This 2 will jump up. So it will be 2 divided by 3. So probability of getting a gold from the first box, because the why first box? Because it contains 2 golds. So even second attempt also we can have. That's what I said. No, what is the probability that the other coin in the box is also gold? So it can be in only first box. So the probability is 2 by 3. Kindly make a note. Yes, dear students, with this finally we have completed. I have completed all the 13 chapters. Detailedly, I have finished the concepts and I have worked out and I have explained. I mean to say, I have explained all the problem from all the 3 model question paper issued by KSEAB. As it is said that 70% of the question is going to come from this model papers. So with this intention, I first targeted PUC aspirants, that is you. So finally, along with you for first PUC also have did, and even we have went for live session as well. So today, with respect to PUC, I have completed, and very shortly we are going to come with CET as well. KSET, as you know, the already dates are announced, April 23rd and 24th, the next month. So I'll be also going to go ahead with the KSET. Already Matrices part 1 is uploaded. Okay, so surely I'll be going ahead with this. So all the very best. Do well, give you 100%, be dedicated and rock. Give you 100% for your final examination. Give your 100% for your final examination and give your best. Okay, all the very best. Do well. And lastly, God bless you all. Do like, share, and subscribe to our YouTube channel, Math Universe with Dr. Naseer Ahmed. Thank you again.